This video is going to cover combined loadings. For combined loadings, all we're effectively going to do is everything we've done before, but sum it all up. So before we had multiple types of normal stress. These normal stresses can add together. Any of them that happen to be going in the same direction add together, and any of them that are going in opposite directions, well, then they subtract from each other. If they're not going in the same exact direction, then obviously they can't add. Also, we had our shear stresses, our taus, and those can also add together. But what you cannot do is you cannot add sigmas and taus and get a mystical third Greek letter. Those are separate. So our different types of normal stresses, as you may recall, we have axial. Axial is a normal force divided by an area. Then we have a bending, and our bending equation is a moment times the distance to the neutral axis divided by the moment of inertia on that neutral axis. And then we also had thin wall pressure vessel equations. But for most of our problems with combined loadings, we're going to just kind of ignore these guys because, well, we're not going to deal mainly with thin wall pressure vessels. However, it is a normal stress, so it would technically add all together along those outside edges. For our shear stresses, we have two types. We have our torsional shear stress, and for torsion, that's T for torque times a rho, distance from the point to the center of the object, divided by J, polar moment of inertia. We also have our transverse shear stress, and that equation was VQ over IT. So that's shear times first moment of area divided by moment of inertia and the thickness. So all we have to actually do is look at our problem, analyze what forces we have, so effectively doing statics all over again, and then pick which situations do we have, which of these equations are we going to use, and then add up our sigmas and add up our taus. That's literally all we're going to do. So here we have a nice example. And in this example, we have a circular pole kind of coming up. It goes up a distance, but the distance that we care about is 2 feet from the top down to section AA. And then at the top of this pole, we put a flat piece coming off here where we cut a little hole and we've attached some, I don't know, maybe strings to it, and we're pulling. So we're pulling straight up in the Z direction up by 4 kips, and we're pulling horizontally in the Y direction there by 5 kips. We want to find the state of stress at A and B, and A and B are on our section AA here. So A is at the bottom. If we were to kind of draw out where that would be on this circular shape, remember since X is over here, this would be A and B would be over here if we were looking at it at part AA. So then we have a radius of 2 inches. So step number 1 of any of these problems is to do the statics. So when doing this, it's kind of important to know which side you're doing this stuff for, because remember, when we make a cut, we do have our forces going in equal and opposite directions for our internal forces. So I'm going to cut along the top here. I'm going to take the top half. So I'll just kind of redraw it here, just kind of in stick figure form. I have 2 feet here down to A. I have 1 feet over. Again, we said we had 4 kips straight up, and we had 5 kips out in the Y. And let's now go calculate out all of our forces. So what forces do we have? We have force in the X. We have forces in the Y. And we would have forces in the Z, because remember, this is a 3-dimensional problem. So X, Y, and Z. And then also, you're going to have moments. So we have moment in the X. We're going to have moment in the Y. And then we're going to have moment in the Z. Now, does it actually matter in which direction we're drawing our arrows? The answer is no, because of course, through statics, we're going to figure out the correct direction for all of these things. So let's start with the forces first. All right, so we're going to sum the forces in the X direction and set it equal to 0. Well, how many forces are going in this direction? Just Fx. So cool. Fx is 0. Next, we're going to go on to, that was ugly, sum the forces in the y direction here and the forces in the y direction. I'll just draw that out. Force in the y direction, so anything going this direction. We have negative force in the y, and then we had also a positive 5 kips, depending on which way we took positive, so we'll just draw it. I'm taking this way to be positive. Force X, I'm taking that way to be positive. Right? It's always good to label which direction is positive. So then we're going to get that force Y is equal to, of course, 5 kips. The fact that my answer is positive does mean that the direction of the arrow that I drew originally over here was correct. So what I'm going to get from my answer over here is that it's 5 kips in the direction that I drew it, which is that way. Okay, so now we're going to sum the forces in the z direction. So in the z direction, I'm going to take upwards to be positive. Why not? And that is Fz going up. Oh, we're supposed to set this equal to 0. Let's put the 0 in first. We have Fz going up. We also have 4 kips going up. So this time what we're going to get is that Fz is equal to negative 4 kips. And all that means is that Fz is 4 kips going in the direction that we did not draw the arrow. So in this case, it's going down. Okay, so that's all that means. And now for the moments. So I'm going to try and, you know what, let's just scoot these forces over so that we can see our moments now. So let us start by summing the moments in the x direction first, set it equal to 0. Again, we have to pick a direction to be positive, and because we're in 3D, you can't just be like clockwise, counterclockwise, because, you know, that depends on which way you're looking. So I'm going to draw the arrows. And again, which direction is this turning? Use right hand rule. So take your right thumb and point it in the direction of those arrows and look at the direction your fingers are curling. That's going to be positive. So which of our forces are going to create a moment about this x-axis? We're looking for anybody who's going to cause rotation this way. And, well, the 5 kips actually is going to cause big ol' rotation that way. So cool. So we're going to have our 5 kips, and it's going to be going which way? Positive, right? Because this was our positive direction. So this is going to be 5 kips positive times the distance that he is perpendicular to the axis, which is 2 feet. Okay, cool. And then what? Well, who else happens to be assisting us with this rotation around x? Technically, this 4 kips is going to rotate the opposite direction about x. So we're going to have minus 4 kips times the distance to that axis, which is 1 foot. And then, of course, we do have mx himself, and he is going in our positive direction. And that's everybody. So moving things around, we have 10 minus 4, so that's 6, but he has to go to the other side. So mx is actually equal to -6 kip feet, by the way. So mx is 6 kip feet, but going that way. Alrighty. How about now, let's go look at our moment in the y. So if we sum the moments in the y, and let's take, of course, our drawn direction to be positive, because that's always nice. Who is going to cause rotation about this axis? So again, using right-hand rule, I'm going this way around. So coming up over the top there. And yeah, who's going to rotate about that? Well, obviously our y force isn't. But even that 4 kips, happens to be directly above that axis, and if you're pulling it directly up, he's not causing any rotation. So actually, we don't have anybody who's not just moment y. So moment y is actually equal to 0. Okay, that's kind of cool. How about moment z? Moment z, again, I'm going to just choose my direction to be positive that I drew. And who's going to be causing any rotation about z? Well, obviously this 4 kips is not, because he's in the line of direction of z. And even this 5 kips is actually in line with that axis. So he's not going to be causing any moments about z. He's actually just going to move the z-axis. So yeah, again, moment z is 0. So we actually have no x force, but we have a y force, we have a z force, and we have a moment in the x. So how about we copy this guy? That didn't really work. We're going to copy this guy here. And we will just redraw down here what forces we had. So the force in the y, we did have this guy. We said he was 5 kips. We had a force in the z, he's going to go down. We said that's 4 kips. And then we had a moment in the x, we said coming out this way, 6 kip feet. Okay, so this is our effective free body diagram. And again, we're going to be looking at what's going on at the bottom of this face. So let's draw it. Remember, we have our axes here. This is ugly, but whatever. We have A on the bottom and B on the right side here. And we do have this 4 kips that's going directly out of that face. So we are going to have an axial force, right? Because it's the normal force divided by the area, and 4 kips is going normal to that face. So we're going to have that our axial force is our 4 kips. He is going away from the face, so that's going to be positive. He is in tension. And then divided by the area. The area of a circle is pi times r squared. What's the radius again? Going back over here, 2 inches. 2 inches. So pi, again, times 2 inches. And then squared, pi r squared. So we're going to get that our axial force is 0.318 kips per square inch. Right, and our 4 kips is going down, and down is, of course, going to be tension. So we should probably write that as tension. Okay, and tension is, of course, positive. Probably shouldn't underline that, it's positive. Cool, and then the next question we have is there any bending? So remember, that's also a sigma, so we have bending. Is there any bending at all? Well, we have this moment x, right? This guy over here, we have moment x. So following right-hand rule, and we are going to be looking at the underside, so you got to keep twisting your hand around to see that technically he's going to be coming off the bottom of this face. He's going to be coming out and then going in. So if I were to draw that over here, he'd be coming out and then going in. And that is our moment x, which again we said was 6 kip feet. Alrighty, so we do have bending. There's no other moments, so obviously we can't have any other bending. So we have our one bending there, and we are bending about our x-axis. So we're going to be having mx here, which our mx was 6 kip feet, times the distance from the point to the neutral axis of bending. So if we're looking at point A, swap to another color here. If we're looking at point A, the distance at point A is to this neutral axis is 0. Yes, he's on the neutral axis of bending, so sigma bending for A is nothing, by the way. And for B, how far is point B from that neutral axis? It is lo and behold, the radius. Remember, our radius was 2 inches. Well, hold up, we got feet and we got inches in this equation, so somebody needs to go. So we're going to say there's 12 inches in a foot. And now we're going to have everything in terms of inches divided by I. The moment of inertia for a circle is actually the same in every direction because a circle is the same in every direction. And that is pi divided by 4 times the radius, which we said was 2 inches, raised to the 4th. Yay, so cool. So when we solve for that, we're going to get 11.5 KSI. However, that is not specifically at any point. That is just the maximum at B. Are we positive or are we negative? Since the arrow is going into B, if we're doing bending at B, this is going to be negative, right? This is actually in compression. Okay, so now if I want to truly find what is the normal stress at A, I'm going to add my axial, and my axial was 0.318 KSI, and my bending at A we said was 0. So my normal stress at A is 0.318 KSI. And it is in tension, kind of important there, it is positive. And if I want to know my normal stress at B, we have my axial, which is 0.318 KSI. It is going across the whole face. And then we have our bending, but our bending on that side is going back into the face. That's negative. It's minus 11.5 KSI. And we're going to get a grand total of negative 11.2 KSI, so that's in compression. You wouldn't obviously write both of them. You would just say 11.2 KSI in compression. So cool, so we found the two normal stresses. Now let's talk about our shear stresses. But remember, for shear stresses, we only have two equations going all the way up here at the top. We have torsion and we have transverse. Torsion requires moment. However, our moment is not creating twisting or rotating of this dude, right? You have to be rotating him in order to have torsion, and that would be a moment in the z, but as you recall, our moment in the z was 0. So we're not actually going to have torsion. Yay. So we just have transverse, because you notice we do have that 5 kips that's going to be going across that face. So let's draw the picture one more time. A here at the bottom and B over here on the side. Our lovely axes here. Awkwardly, X is vertical, but that's okay. And we have our 5 kips, and he's going along the y-axis. Yep, 5 kips, and he's going along the y-axis. Kind of awkward, to be honest. Now you might be thinking, whoa, shear doesn't normally look like that. What did it normally look like? Well, let's just rotate the page a little bit here. If we rotate our picture and we put A over here on the side and B on the bottom, and now this is looking more normal, right? We have an X and a Y, and then we are still going away from B, still going up 5 kips. Does he now look normal? Quote unquote normal. Okay, so now hopefully you don't feel like this is a really bad equation to solve because you've seen this one all the time. Right, we have our transverse shear stress, and that's VQ over IT. Cool, so he looks just normal now if you just don't look at this guy. But if you look at our rotated one, feel free to always rotate the picture, right? Anytime that it would help, rotate the picture. So here we go. So he looks normal. So our V is 5 kips. Our Q, well, that depends on which one we're talking about. So Q, let's talk about point B first. Q for B. Again, how do you solve for that? You're going to draw a line across at that point, bam, right there, and then you're going to take the area away from the neutral axis. That's over here. How much area of the circle is there? Nothing. Yes, QB is nothing. Isn't that lovely? So we're going to erase all that. So QB is 0. And Q at A, let's do it with, how about a highlighter this time? They're easier to erase. So we're going to draw a line right here, and then we're going to take the area away from the curve. And away from the curve would be either up or down, so this area, which is a half a circle. So cool, so QA is going to be that A prime is a half circle, which is half of pi times the radius squared. All right, so this is our A prime. And then our Y bar prime is from the centroid of this half a circle down to the neutral axis, and that distance is, go look it up in your textbook, correct? That's going to be 4 over 3 pi times the radius, which again was 2 inches. So this is our Y bar prime, our A prime, there we go. Put that together and we're going to get a grand total of 5.33 inches cubed. Yay. So we have Q, I we already know, we knew the equation, we just moved it up there somewhere, and T is the thickness. So again, even if you were uncertain about B and you messed it up, what's the thickness of the circle at this point? Technically 0. Technically 0, so you would have 2 ways that your equation would not work. Yeah, one of them is going to be undefined because, again, you can't divide a number by 0, but that should tell you, hey, something's wrong. However, that the width, though, over here, the thickness at A is simply 2 times the radius. So again, our transverse at B is 0 for 2 reasons, because Q is 0 and the thickness is 0. 0 divided by 0 is grand total 0. So our transverse at B is 0, but our transverse at A, we have V. V was our shear was 5 kips times Q. Our Q here, 5.33 inches cubed, divided by I. Remember I for a circle, same in both directions. Pi divided by 4 times the radius of 2 inches here, raised to the 4th. And then times the thickness. The thickness was 2 times our radius, which was also 2 inches. So what we're going to get for the transverse stress is 0.530 KSI. So again, is it positive or is it negative? Well, let's go back and look at the direction that our arrows are going. Okay, normally when we talked about our internals being positive or negative, we normally didn't draw them with a vertical member. Normally we drew them with a horizontal member. So we have a vertical member here that we broke in the middle. But again, if I just kind of rotate this horizontally in there. So again, we're looking at this guy, who again, if we just rotate, is this guy. And remember when we were drawing our shears, on this side, it's up, out, and around. So our shear is actually positive across this face. So when we come back down here and we write that our transverse, or our shear stress actually at B is only the transverse because there's no torsion, it's 0. But KSI will have units. And then for A, our shear stresses, there's no torsion, but it is going to be a positive 0.530 KSI. We can't really say tension, we can't really say compression, that's more of like a normal stress type thing, but we can say whether or not it's positive or negative, and that again is just telling us the direction of our stresses. So you see, it's actually not too complex. It's simply the same problems you've been doing over and over and over again, except now we're just bringing it all together all as one. So again, we need to first up do statics, actually figure out all of our forces, and then see, as like each individual separate problems, which direction those forces are going to create stresses, and then if they add together because they're both positive, cool, and if they don't add together because one's positive and one's negative, well, just watch your signs. The only thing to really pay attention to is mostly with our shear stress, and you want to make sure that your direction for your arrows are obviously going the same direction. So it's always good to like draw a picture of the arrow distribution to make sure that you're looking at it in the correct direction. So anyway, that's all there is for combined stresses. So hopefully you don't find it too difficult.